Hi, my name is Chris Barnes,
I'm Chris Butler.
and we're with Project 17, which is a logic analyzer oscilloscope integration which runs through USB port on a PC.
Logic analyzers and oscilloscopes are common tools in electrical engineering labs. However, they can be very expensive and complex. Our device is easy to use and is intended for electrical engineering underclassmen. It has a simple PC user interface which allows the user to control the device and view data. It is so easy to use that you can start measuring signals in under 30 seconds and costs less than $120.
We will now discuss the engineering requirements for our project. There must be a variable sampling rate. Where the logic analyzer has a maximum sampling rate of 8 million samples per second, and the oscilloscope is required to have at least a 700,000 sample per second sampling rate. There must also be a graphical user interface, which is easy to use and provides students with the waveform that they are measuring, and also gives them the ability to control how the device is being measured. There will also be cursors, which will allow the students to measure the waveforms that they are currently capturing. The device will also provide the students with 4 control signal outputs, which will be ground, 1.8 volts, 3.3 volts, and 5 volts, as is typical with digital signals. The user can also control how data is triggered off of either the rising edge or the falling edge. We will also provide the students with a useful voltage input range of plus or minus 25 volts. The input range could be as high as 60 volts with minor hardware replacements. The device must be affordable for students, costing no more than $300. And it also must be solely powered via the USB on any typical computer, thus requiring a maximum current draw of 500 milliamps. The circuit must also be implemented with PCB, and the device must also be durable, able to withstand a drop from 3 feet and also survive inside of a student's backpack. I will now describe an outline of topics we will discuss using this very general block diagram. We will first discuss the oscilloscope attenuation circuit, which is the first process the incoming analog signal goes through. Then we'll describe how the PSOC microcontroller samples and collects data from the waveform, followed by how that data is processed and displayed onto the graphical user interface. We will then describe the logic analyzer's protection circuit, followed by how the logic analyzer samples the incoming logic signals. We'll also describe the control signal circuit, which provides the user with variable output voltages and the option to trigger data capture using signals provided on board the device. Finally, we'll talk about how digital logic data is processed and displayed on the graphical user interface. We will conclude our presentation with recommendations for future senior design students.
The front-end attenuation circuit has been specified to take an input signal between positive 25 and negative 25 volts. Furthermore, it must protect against a 60-volt amplitude user error. The input must be shrunk to a microcontroller safe range of 0 to 5 volts. The front-end attenuation circuit takes an input signal and attenuates it by a factor of 20 through a voltage divider of resistors and capacitors. The signal is given an offset to keep it between 5 volts and ground. The signal then is passed through an op-amp to isolate it from the device input. Finally, the signal is passed through a programmable gain amplifier so the device can accurately measure any specified signal amplitude. This final signal is what is passed to the analog to digital converter in the microcontroller.
Next, I'll be describing how the PSOC microcontroller collects oscilloscope data, followed by the functionality of the triggering mechanism used to activate data capture. The incoming analog signal first enters the analog to digital converter, or ADC, which then produces 12 bits to describe the voltage level of each sample. Once it's done converting the analog signal into digital data, the ADC produces a pulse, which tells the DMA, or direct memory access, which automatically will retrieve that data and transfer it into memory. The DMA continues to automatically grab data and move it to memory until 2,000 samples are collected, at which point an interrupt occurs, telling the PSOC to send the 2,000 samples to the computer through USB. Multiple trigger options are also provided. The digital to analog converter, or VDAC, provides a voltage to the comparator such that when the incoming analog signal from either channel 1 or channel 2 reaches that voltage, the output of the comparator changes state from either high to low, which activates a falling edge trigger, or low to high, which activates a rising edge trigger. This state change then causes the flip-flop to output high, allowing the end of conversion pulse to tell the DMA to retrieve data automatically from the ADC.
The oscilloscope has a very simple graphical user interface which allows the user to control how the device measures signals. The user can control how many channels are active and the resolution of both amplitude and time. The channel, edge, and level can be specified for the sample trigger window. On the oscilloscope graph, the user can use the grid to observe time and voltage measurements. Cursors are provided for more accurate readings. The GUI receives data and sends commands to the device over a standard USB COM port. Alright, we're going to demonstrate the operation of the oscilloscope. You can see the device is connected to the computer via USB cord. And to channel 1 we have a 10x probe where we are measuring a 1 kHz square wave with a 20 volt amplitude. To launch the oscilloscope we click the launch button, and when we get all the windows in view, we can turn the function generator on and click enable on the channel 1 view. And now we have a square wave, and if we tell the trigger to trigger off the rising edge, you can see it smooths out. And we can amplify this wave and see a very cool waveform. And if we change the edge of the channel, you can see that it flips, showing that it is indeed triggering on both edges. And we can also zoom out or lower the sampling rate by clicking on that button, and we see more waveform or more periods show up. The logic analyzer input protection makes sure the microcontroller does not get damaged. It provides an overvoltage protection below 0 volts and above 5 volts. It also provides protection against overcurrent and electrostatic discharge events. First encountered is a current protection resistor followed by clamping diodes. At this point, the signal is sufficiently protected to be sampled by the microcontroller.
I will now discuss the logic analyzer data collection and triggering, followed by a control signal functionality description. The VDAX function is similar to that of the oscilloscope, providing a voltage which must be overcome to register a high digital level. The incoming logic signals then enter flip-flops, which store the current state, which is either high or low, on the rising edge of the clock input. Once 2 sets of data are stored in the top 2 flip-flops, a clock pulse is sent to the FIFO, which stores the bytes. Once 4 bytes are collected, a pulse is sent to the DRQ terminal of the DMA, similar to the oscilloscope, which transfers the bytes directly to memory. Upon filling the memory buffer, an interrupt tells the PSOC to transfer the buffered data to the computer through USB. The trigger for the logic analyzer only exists on channel 0 and works similar to the oscilloscope. Once triggered, the bottom left flip-flop goes high, which enables the FIFO. Unless enabled, the FIFO will not store data. The control signals use a counter, which on every clock cycle increments the count. Once the count reaches a specified value, a pulse is generated, which activates the flip-flop and sends a high digital signal to a lookup table. The lookup table has pre-specified inputs and outputs such that each combination of inputs activates a specific output. The state change of the flip-flop causes a high output, or rising edge, to occur on the top control signal, and a low signal, or falling edge, to occur on the bottom control signal. The difference in the bottom control signal is caused by the inverter, which is present on the output of the flip-flop.
The logic analyzer GUI provides the same function as the oscilloscope GUI. The user controls which logic level the device responds to, how many samples are to be taken, and at what rate the samples are taken. A trigger can be set to respond to an edge to control when the data sampling starts. Data is received and commands are sent through the same USB port as the OSCOPE GUI.
Oh, hi! Today we'll be showing you the functionality of the Logic Analyzer. Right here we have the Logic Analyzer probe. That's hooked up to the signal generator, which was producing a 50 kilohertz square wave. And the other set of probes is for the control signals. You start by launching the Logic Analyzer. We'll be collecting samples on channel 1, which is displayed here. We'll be taking 500 samples at 10 million samples per second. Click go. And here's our square waveform. To prove that we have multiple sampling rates, at 5 million samples per second, you'll get fewer samples of the same waveform, so they'll be compressed and there'll be more of them on the screen. Going back to 10 million, we'll now show trigger functionality by enabling the trigger on the rising edge at a 5 volt logic level and using channel 2 at 5 volts to trigger. It will take 3 seconds from now. As you can see, on the rising edge is where it was captured, and if we want to use the falling edge instead, we choose falling. We can use a falling edge control signal, which we will be using channel 3. Set channel 3 to 5 volts, and go. And as you can see, it was captured on the falling edge, low, then high. That should prove functionality for the Logic Analyzer. I'll now go over the recommendations that we would make for future senior design students. It's important at the beginning that if you do not know that something will succeed, to choose a specification that you know you can meet. It is also important to order all your parts and your PCBs early on so that if something doesn't work or you need to do a parts change, you have time to purchase new parts. It's also important to start planning early on and getting a full understanding of what your project is going to entail. The last two are the most important. One is beware of scope creep. It's important to maintain specifications that can be met and to stick to those specifications and don't overreach your bounds. And most important, keep an open mind. Other members of your group have great ideas, and you need to be willing to listen to them and change ideas that you may have based on things that they say, and not try to maintain full control of the direction of your project. We've discussed the features of the oscilloscope as well as the features of the Logic Analyzer, and we have also discussed some of the recommendations we would make for future senior design students. Some other features we would have liked to have implemented given more time is the use of a faster USB chip so that we could have used the high-speed USB protocols. And we would have also liked to extend the features of the control signals.
We would also like to have a hexadecimal view of data on the Logic Analyzer and use the extended feature set of the PSOC.
We would like to extend a special thanks to Rosie Gusky for her help with the Logic Analyzer and Oscilloscope project, and also Stephen Dans with Cypress Semiconductor, who has sponsored our project. This is Project 17, signing off.